So today we're going to cover about quantum complexity classes. So before that, we try to cover what is the meaning of Turing machine and all those stuff. I welcome you all for once again for this wonderful faculty development program series about quantum technology. We are at QT02 Foundations of Quantum Technology. So let's start with today's topic. I try to start with quotes. In natural science, nature have given us a world and we are just to discover its law. Okay. In computers, we can stuff all these law into it and create a world. So this is very beautiful portrait about why we need to have computer, why we are using computer to do such computational tasks. Okay. So whatever the rules, the regulation across the nature, we try to simulate and emulate in our little systems. Okay, we can create our own world in such a way. So one more beautiful quote, our field is still, it is in embryonic stage. It is great that we haven't been around for 2000 years and we are still at a stage where very, very important results occur in the front of us. Okay. So even though we evolved millions of years, but within the past 100 years or 200 years or very right now, we went through so much of technological advancements. Okay, whatever we are thinking, whatever we are doing, it is unimaginable before 100 years. Okay, we are going at very fast rate. To understand the quantum computer, we need to understand the complexity. Okay, so that is the given topic today. If we are able to understand the complexity, then we can understand how quantum computer will help you to solve this problem. Okay, so we try to solve a lot of problems using classical computers so far until today. But today's motivation is there are intrinsically hard problems that today's computer cannot handle. So if you want to study quantum computer or if you want to use quantum computer, you need to ask this basic question. Why we need to use quantum computer at all? To solve very, very hard problems. So some problems are intrinsically hard. We cannot solve using classical computer. That is why we go for quantum computer. To understand that, we need to understand computability theory. Okay. If a problem is there, whether the problem is able to compute, able to solve. Okay. So this is predicted by three mathematicians, Craig Gödel, Alan Turing, Alonzo Church. These three mathematicians, concluded that some basic problem cannot be solved by computers. Some basic problems also cannot be solved by computers. We will check what kind of problems they are. Okay. So one such problem is determining whether a mathematical statement is true or false. So this is very, very easy for a small kid, right? So small kid can be able to say whether it is true or false. But if a computer need to do that, you need to train that computer, you need to give inputs. So this is what we are doing in AML. Okay. So computer cannot think on its own. Even a simple mathematical problem like true or false, it cannot decide on its own. Okay, on own. This is very important. If you're giving all these predefined data, it could take decision based upon the data. But if there is no such kind of data, computer will struggle. Whatever computer if you are creating, it will struggle. Even the quantum computer will struggle. Okay, some problems are never ever able to solve by computers. So though it seems this kind of problem can be solved by computer because they strictly lies within the realm of mathematics, no computer algorithm can perform this task. Okay, unless or otherwise, if you are giving some pre-trained data or you are giving perfect instruction, the computer cannot take decision on its own. Okay, so this situation results in a development of ideas pertaining to theoretical model of computer in which turn may lead to the construction of actual computer. Okay, so this is very good part. If people are from mathematics, they able to see this, able to witness their contribution. Okay, so initial stage computer science evolved from theoretical side. Okay, theoretical computation side. So all kind of problem not able to execute in practical way. So how it will evolve? First, it will evolve from theoretical aspects. Okay. So here the mathematics played a vital role actually developing physical computer. So this is one kind of concept. The Turing machine is an abstract machine. Okay. To understand how the Turing machines work, we need to understand the basic terminology. So this is for non-IT and CS people. So algorithm as a process or set of rules to be followed in calculation or other problem solving operations, especially by a computer. So it is, you can consider it is previous stage to a program. Okay. So you need to have some algorithm. That algorithm defines a process or what are the rules you need to follow to do some particular task, to solve particular problem. Okay. So in plain English, you can say this is nothing more than series of steps that turn some data into more desirable form. So sometimes you need to process your data, input data. So most of the time we are not able to solve in straight linear way. Sometimes you will get intermediate results and you need to wait for some more time to get more data accurately to process. In those steps, okay, your data, input data is turned into some more desirable form. It could be your answer, it could be your solution, it could be intermediate results, it could be any form, what you want to do with it. Okay. So if you consider all these points in your mind, the Turing machine is not actually a machine so much as an abstract model of computation. So whenever we are talking about Turing machine, it is not actual physical model, it is a abstract model, or you can say mathematical model. Okay. And it never implemented in hardware, real-time hardware, but most of the computer hardware are based upon this abstract layer or abstract constructions. Okay. So computable theory comprises computability and complexity of the given problem. Okay. First, we need to understand whether the given problem is computable or not. If it is computable, what degree of complexity involved within that? Okay. The objective of complexity theory is to classify problems as easy one and hard one, where computability tends to classify problems as solvable or not solvable. So two different kind of category you are able to see. If you look for entirely complexity theory, so you can categorize easy problem or medium problem or hard problem or very hard problem in such a way. Suppose if it is solvable, okay, then it belongs to all these categories, right? So it introduces many concepts. Again, it is a mathematical model used for computable theory. So whether a typical computer can do, but it cannot be solved some problems that are beyond theoretical limit of computations. Okay. So even though if your computer or supercomputer, some problems are never intended to be solved, right? So you need to decide. You need to decide whether your computer is able to do or not. You are able to check with the help of this Turing machine. If Turing machine is able to solve, your computer definitely able to solve. So at what point you able to decide this? You need to investigate in power of algorithms to solve problem. Okay. Each and every time you need to increase your input data and you need to measure whether you are able to achieve the computational power or resource provided for that problem given. Okay. So it is also necessary to know the unsolvability of some problem. Sometimes if you took some problem which is not able to solve at all, if you don't know that, if you keep on trying to solve that problem, all your time, effort, resource going to be in vain. Okay. So before conducting any computational research, we need to do this computability theory. We need to apply complexity theory. Then you need to decide whether your problem is feasible to solve or not. Okay. So how we can able to do that? We are able to do that with the help of reducibility. So this is a mathematical technique. we are able to break down our problem into smaller chunks, and we try to solve a smaller chunk initially. If it is solvable, okay, then you can go for the larger scale. So what is the meaning of reduction? Reduction is a way of converting one problem to another problem in such a way that solution to the second problem can help solving the first problem. So it is like you can compare this reduction in the terms of differential calculus. Suppose if you have very big problem, if you are not able to solve in the first iteration, what you are able to do, you are taking a smaller pinch out of a bigger problem. Okay. Again, that smaller pinch is very difficult for you. Again, you go for second order derivation. So it is, you can imagine in this way. So this is the given problem, very big problem, given problem. So you can say very big to solve. Okay. So what you're doing, you're taking a smaller pinch out of your problem. So this is first order derivative. Okay. So this is first order derivative. Again, this first order derivative is difficult to solve. Okay. You're taking a small portion out of this. You're taking a small portion out of this. So this is second order. Okay. So likewise, you're taking a smaller pinch out of each and every uh, given problem. Once you're able to solve, you will get accurate result. You get accurate result. You try to apply the integration reverse process. Integration reverse process. Okay. So you know where you took from. You apply that limit from lower limit to upper limit. You're able to know. Then you apply the double integration to reach the original given problem. So how many derivations you are doing, you need to do in reverse order to do integration. Okay. For a simple example, if you cannot repair an electrical fan, if you don't know about how electrical works, so this problem tends to be unsolvable for you. Okay. So not every one of us able to repair a electrical fan. We are coming from different domain and we possess different knowledge. Okay. So for that, what we are doing, we try to find an electrician. Suppose once he got an electrician, he able to get repaired. So finding the electrician is a second problem. So the first problem is you are not able to solve. You are not able to solve. The second problem is finding the electrician. Okay. If solve the second problem, then you are able to solve the first problem. So what is the basic problem? Repairing an electric fan. Okay. So this is the first problem. So if you're able to solve the second problem, then you're able to solve the first problem. So if your problem have dependency, then you are able to solve from backward process. So to do that, you need to do regression theorem and logical theory and other aspects of computational theory. So basically, you can visualize computability theory in 4 different ways: Turing machine, decidability, recursion theorem, and reducibility. If you're able to achieve all this stuff for a single given problem, then your problem is doable. You're able to decide your problem is doable or not. Okay. So how to identify the given problem is difficult or not? By asking sample questions. Okay. So look at this. Look at this riddle. Yes. Please put your doubt in the chat box if you have any. Screen is visible. I hope screen is visible for all participants. If it is not visible, just rejoin. The screen is visible for all? Yes. Yes. Thank you. Thank you. Okay. So look at this riddle. Look at this riddle. So what could be the answer for this riddle? I try to zoom. Look at this riddle and try to answer this riddle. We will cover once again with the diagram. We will cover once again. Anybody able to predict the answer? Can anybody able to find the answer for this? Can you put in chat box? Very easy. Secret. Yes, ma'am. Very good. So this is about secret. Okay. So the next type of question is playing Tetris. So the first problem contains a straight answer. The second problem contains multiple combination, means multiple answer. Yes, random probability. Okay. The next problem contains solving numerical problem. Okay, you can solve numerical problem in multiple ways, but answer is remains same. Okay. So each and every problem have different level of complexity. So based upon the complexity, able to segregate. The first one is very easy. When compared to the first one, the second one is little difficult. The third one involved with numerical aspects. So the first one is based upon text. The second one is based upon geometry or pattern. The third one is based upon numbers. Okay. The fourth one about playing chess game, which is completely different from the previous problem. Okay. So it is the combination, you can say, with playing with Tetris involved with multiple options. So here also multiple options. Okay. Multiple permutation and combination. So changing one coin, one step will change the entire game scenario. Okay. Much more complex. Then compare Sudoku. So which is equivalent to playing chess as well as equivalent to playing Tetris, but it is based upon numerical. So in chess, there is no numerical, but in Sudoku, we have numerical. So answer is only one. In Sudoku, answer is only one. But the different way you can solve that problem in different dimensionality. Okay. So look at the comparison. Playing chess is difficult because the game can change into any pattern. But solving Sudoku, the final answer remains same. Whoever solves. Okay. But the way they about to solve, the time taken to solve will vary. Similarly to chess. If they are not keeping time, chess will take 1 week, 2 week, 3 week, or even years. So during ancient days, if king don't want to lose, he can play chess for months, even months. Okay. The last one is very, very interesting, counting grains of sands. Okay. So this problem seems to be possible in theoretically. You can count grains of sands theoretically. But if you want to do practically, it is almost impossible. Okay. So most difficult problem in computer science are related to the last example what we are about to observe. Okay. So even though theoretically you're able to solve, but practically it is almost impossible. To get a solution, we need to ask multiple questions with computer. So does solution exist? If solution exists, what we supposed to do? Okay. Whether an algorithm exists for your solution. Okay. So if an algorithm exists, then you need to ask how many steps it will take, then how long it will take, then how much resource it will take. So finally, you need to ask, does your program eventually stop? Suppose if your program not eventually stop, you never able to arrive your solution. So this is one interesting problem in computer science, halting problem. Suppose if you keep on running a program without any break, if program doesn't break, so it leads to infinite loop. So you never ever able to achieve your solution. Okay, this is most important question. So once you got answer for all this stuff, then you know to ask whether your solution is actually efficient or not. Okay. So in simple terms, we will say, yeah, solution exists, a program exists, a product exists, but we need to ask whether the solution or product, how much efficient it is, that matters. Okay. So difficulty of too many steps. Take an example of given task, baking a cake with given ingredients. The given ingredients is only 3 or 4. You are easily able to make a cake. Okay. But if a given ingredients are 12 to 12 different combinations, then the complexity become increased. Okay, the task is same. Baking a cake with 2 or 3 ingredients is very easy, plain. But if a given ingredient is more than 12, okay, it becomes more complex. The process remains same. Similarly, multiplying numbers. If 3 given numbers are get multiplied, it is very easy for you. But if I'm increasing to 100, the same problem become more difficult for you. Okay. So here it is doable, but the difficulty is increased so much. The next problem, like sorting books by given title. Take an example of piles of book over your desk. So it is very easy for you. But if I ask you to sort a full library, the same problem become much more difficult. It will take months, right? For a few persons, it will take months. So it depends upon the book volume. Okay. Similarly, if you want to solve a Rubik cubes, 2 cross 2, very easy. Even children can do. But if I'm increasing 8 cross 8, even a professional will take millions of years. So practically impossible. So why we choose this topic? So on solving problems. Okay. So normally computers are used to solve problems, but the quantum computers are used to solve very difficult problems. So that is why we arrived for quantum computer. Okay. So normally we can tackle difficulty with trial and error. Okay. Suppose if you have suitcase, so suitcase have some passcode. Okay, based upon the 4-digit numerical lock. If you forget that lock, if you forget that pattern, what you're supposed to do, you will start from 000 and you try to increase one by one. Okay, you you can do randomly also, but if you do randomly, you don't know what sequence you already tried. So that is why we will do sequential search. Okay, so at one point of time, you're able to crack. So this is exactly what we are doing, trial and error. So each time we will do trial, then we'll observe our output. Okay, so each time we will do trial, we'll observe our output. If our output is correct, then we'll pick it up. Otherwise, we'll try to reduce that error. Suppose if your solution is 997, imagine you are starting from 0000. Okay, imagine in this way. Okay, so you tried all 996. It means these are your trials. If you do these many trials, your error rate will get reduced. Your error rate will get reduced. So more trial you do, the less error you will get in subsequent approaches. So this is the logic. So each time we will do trial, and each time we try to reduce of our next result. Okay. So take an example of finding a needle in a box. So it is very easy. A box is very small. But if you want to find a needle in a very big haystack, okay, so cattle haystack, it becomes more difficult for you. The problem is same, but depends upon the situation, the difficulty will get increased. Okay. Take an example of finding prime factors of 91, easy for you. Okay. If I increase 4-digit number, okay, even experts will take a lot of time. Okay. If you increase your input in this case, the problem become more difficult. So in first problem, depends upon the situation. Here depends upon the input size. So third one, we are finding a 3-letter pattern in very long sequence. Suppose if I gave 100 sequence, the same problem might feel very difficult, very hard. So difficulty not only comes with input or data sequence, it comes with their own device. Okay, take an example of memory in computer science, or even memory with our brain itself. Okay, suppose if I'm giving a finding matching pairs, so this much of matrix array. If I am showing pairs, we can identify how many pairs are there. So here you have only two pairs. So two cats and two frogs. Okay. So immediately I'm jumping to previous. If I ask the same question, you need to remember what I showed before, then you need to answer. Okay. So this is quite easy because the matching pairs are very small and limited and in scattered way. Suppose if I am showing 500 or thousands of pairs, okay, very difficult for you because you have very limited amount of memory, you're not able to recall each and everything. So same problem exists with our hardware. Okay, our hardware comes with always limited amount of memory. Okay, especially for hard problem, for very big size of input, we need to do memory management. So keeping a small number of list in our memory is very easy to do shopping like 3 items. But if you go for 500 items, definitely you need to have a very big diary and you need to have a checklist. Once you purchase, you need to tick. Otherwise, you cannot trace back, you cannot remember each and everything. Okay. The same thing happened for computer also. So computer also need to track how many data it process and how much it need to do so. So difficulty not only comes with your input, not only comes with your memory, it also comes with options. Okay. So look at this example. So we have a person at one end and we have maze in between and we have a rewarding golden bag, a golden coin bag at other end. Okay. So if this person want to achieve this solution, which is very best solution or desired reward, okay. So intermediately you will have lot of options. So take an example of orange juice or at one end a ghost is waiting for you. Okay. Suppose if you end up with this orange juice, okay. So this is optimized. optimized. So this is best. Okay. So this is error or wrong. You can imagine in that way. For the same problem, you have multiple solutions and the desirability of solution will vary. Okay. So this type of problem is called optimization. You cannot reach your best, at least you will reach any intermediate result which will benefit for you or suitable for you. Okay. So this type of problem we covered in computer science. What is the short route in across n number of cities, right? So we can do optimization in these type of problem if you have multiple combination and permutation. So this is an example for playing hangman game. Okay, so it is like word game. Two-person need to do. Two-person need to play. If you're able to identify the given word, then you can rescue a person to be hanged. Okay, this is very interesting game, and you can correlate this example to a password, cracking a password. Suppose if a given username, you know that if you want to identify what could be the password for that user, okay, you can have this combination like 85 keyboard characters are there, and normally the password length will be 8. And how many calculation you need to do? You need to raise 80 power 85 to the power 8. It is almost impossible. Even supercomputer will hang. Okay. So why this happens? Because each and every letter have different set. Take an example of numbers. A single character can involve with numbers 0 to 9 or A to Z or A to capital Z, or it could contain special character. So if we keep on adding character set, the complexity also increases multifold. Okay. So how your problem goes? So to understand this, we need to start from Turing theory. Okay. So this is Turing machine. Okay. So Alan Turing is a great mathematician. He came with an idea in 1936 with a model of computation that still we are using today. So it is nothing but our computer, right? So all our computer, mobile, supercomputer will based upon this Turing machine. It consists of infinitely long tape. Okay, this tape contains instruction and a machine with the state that reads and writes symbols on the tape. Okay, so this is infinite length. This is infinite length. Okay, so here we are able to write data, which is the input, where we are able to read data. Okay, we are able to read data, so which could be your output. Okay, so whatever you computation do, you need to store over here. Store over here. So have some machine. So this machine will read data from this magnetic tape. It is like audio tape. So earlier days, all of us know we have audio tape, so audio cassette tape. So these songs are recorded over there, okay, in sides of the tape using this magnetic tape. Okay, the same idea. Okay, here it is a long paper or tape you can consider. Okay, so whatever this Turing machine able to do, the modern machine able to do, your computer able to do. So whatever this Turing machine not able to do, definitely your computer not able to do. So logic is simple. You can write data in this magnetic tape. Okay, you can do process. You can read from the tape. You can do process again. You can write over the tape. Okay, so here this tape contains both data. So this tape contains both data plus instructions. Okay, so with the help of your machine, what you can do, you can able to read your data and able to write your data after your computation. The same thing you can do over here in this tape. Okay, this will lead to church Turing thesis. So if you are interested, go and find out this church Turing thesis, which is the fundamental question about computational intelligence. Okay. The next thing we need to identify how an algorithm become an efficient one, or how you can say whether your solution or algorithm become efficient one. Okay. So if your algorithm achieves your goal in fewer number of steps, it is very, very efficient. So it is very ideal case. Okay. So nothing happens in real environment. So if you are writing code, it will take some more, much more resources, some much more time because it involved with dependency. Okay. If you're efficient, if your program is efficient, if you want to conclude, it should run faster. It should use less resources, even though if it is not ideal, but it should always maintain less resources. So efficiency is independent of your hardware. It is independent of your implementation. Okay. Then how you can say efficiency? You can say efficiency depends upon input size. And when you increase your input size, how much runtime will get slower or how much resources it will consume. Okay. So if you ask this question, if you try to measure this, it leads to time complexity. Okay. So how you can say your program is very good or very fast? You need to increase your input size. Then you need to measure each and every time. Then you need to plot that. Okay. So to identify any computational resources, it could be fuel for your algorithm. Okay. We need to measure time. Then we need to measure how much space it will require. Okay. Memory space in this term. Okay. How many randomness it involves. So normally, for most of the problem, what we do with our computer science in theoretical aspects, We won't consider randomness. But if you involve with some physical system, okay, always randomness is involved. So much of noise is there, okay, so much of extra things will add upon, okay. So dynamically it will change. During that time, randomness will come. So if you want to do communication, how many communication it will require between components or between machines, okay. So you need to consider all this stuff. Here quantum physics will come. Suppose if your problem involved with randomness, your quantum physics will come, right? So also if you want to do some task in parallel fashion, okay, if your computer have limited amount of memory or limited number of processing cores, then you cannot achieve parallelism. But whatever you do in quantum, each and every operation could happen in parallel way. So quantum processing or quantum computing is true parallel. Okay, whatever you do with normal computer science, most of the time we are doing in sequential because our machine is not that much equipped. Okay, so if your process is independent, if you are able to separate, all your data can processed parallelly in quantum, not sequentially. Okay, so based upon the time taken for your problem, if your problem takes polynomial time, then we can categorize P class. Okay, a problem is in class P if the running time of the best algorithm grows as the power of your input size. Suppose if your input size is n0, then next iteration in it increase n power 1, n power 2, n power 3, keep on increasing. Okay, so these type of problems are predictable. Class B problems are solved in achievable and reasonable amount of time. It is computable and able to predict the time also. So this is very important. Okay. So most of the problem you're able to solve with your desktop computer, with your smartphone, belongs to class B. Take an example of finding routes in your Google Map or searching any file within your laptop or system or playing games. So which is doable. Which is doable. Okay. So all these simple calculation, mathematical calculation, whatever you do with your calculator or Excel sheet, okay, or any kind of software, which is doable. Okay. Sorting a given number or data set, even a large data set you are able to sort, okay, which is doable. Solving a simple Rubik cube. So here you need to notice. Okay. So same Rubik cube could be a very hard problem, but input size is very small. Even your computer able to solve it. So the second class of problem is non-deterministic, which is NP type, okay, non-polynomial type. So these problems appear much harder than P, but taking far long to solve. So little difference is there. Okay, a problem is in class NP when its solution can be easily checked. Okay, if you able to solve a NP problem, if you got the result, you can verify that result in polynomial time, but you cannot solve that problem in polynomial time. Okay, so this point is very important. Okay, so you cannot solve that problem in polynomial time, but the answer resulted in that problem you can verify in polynomial time. So even though it belongs to non-polynomial time. Okay, because NP problem involved with lot of possibility. So if there is a single straight answer which belongs to class P, there are multiple possibility, multiple combination, it leads to NP class. Take an example of factorizing a number. Okay, so factorizing a number, you can solve that problem, but you don't know when you're able to solve because it involved with multiple computation. So randomly you need to check. Otherwise, you can do sequentially, but you need to try all sequences. Okay. So packing a suitcase, a very easy example for us. Okay. If same number of items are given for different kind of people, same kind of suitcase, each and every person will pack in different way according to their mindset, according to their willingness. Okay. So for some person, suitcase is not enough. For some person, they will efficiently pack. They will find much more rooms to put some more objects, because the way they arrange items differ from each other. Okay, that is why it belongs to NP. Sorry, a NP class. Solving a Sudoku. Okay, the same problem is given for different people. They will take multiple approaches. Even the same problem given for the same person at different times, they will solve in different ways. Okay, that is the beauty about NP class. The next category is not polynomial time. So this is a little tricky, little tricky. You cannot solve that problem in a given time or a predicted time. Neither you cannot check that answer in a predicted time. Okay, a time given. Okay, so there is no proof. Even there is no proof. Take an example of playing Go game, which is similar to chess, which is a Japanese game. If you have time, please go and watch this game. Okay, so this type of problem you cannot solve in particular amount of time, and you cannot check the result. Okay, if the chessboard is very large, you cannot check also. For normal, whatever the size we are playing at games, it is verifiable. But if you increase the size, you cannot check. Even using a supercomputer, we cannot check. So I try to give a very good results for you. If you are interested in complexity theory, so complexity zoo website is there. So whatever the complexity class is there, they listed out in this website. So if you are interested in computability theory, or if you are interested in mathematical aspect, you can visit this website. If you are involved with theory of computation, please go and refer. So all categories are given there, which is very, very interesting. So we try to cover P versus NP. So class P efficiently solve problem, where NP efficiently verifies the given problem. Okay, so you can imagine P is a subset of NP class. So whatever the problem available in P, definitely available in NP. But whatever the problem belongs to NP cannot explicitly available in P class. So you can ask this question, whether P equal to NP, can efficiently verified problem can be efficiently solved? So this is very interesting question. There is no proof. So even though they believed P is not equal to NP, but there is no mathematical proof. If you're able to solve, they will offer $1 million. So much of mathematical problem, okay, which is very important for quantum computation. So they are awarding prize, they are giving so much of reward. Okay, so have a glance and promote this among your students to go and check playmath.org. I'll share that website link for you. So this is a mathematical institute. At least we are able to know what kind of problem they are focusing in mathematics. So this is what we are discussing. So we keep on increasing our problem size. So n belongs to log, okay, uh, and n log n belongs to somewhat linear, and n square belongs to square function. If you keep on increasing your input size, your time requirement and memory requirement will keep on increase. So try to increase the power. Okay, instead of square, increase to n power 5 and 2 power n and 5 power n. Each and every time the complexity increases. If you keep on increase the complexity, okay, the normal problem are not visible. So n log n are not visible for us. Okay, after some point of time you can clearly see the difference if you keep on increasing the input. Some problem you can notice this yellow line. Okay, initially it appears initially it grows faster when compared to green line, but after some point of time you can see that intersection. Okay, so only you know the real complexity of your problem if you keep on increasing your input. So after some input size, you definitely know the real face of that problem. So this is one important thing in computer science. You cannot judge the class of problem immediately. You need to wait for some time. You need to keep on increase your input size. Okay, so this is what I am talking about. Okay, sometimes polynomial growth will be greater than exponential growth for smaller input size. Okay, after a certain point of time, you can see the real face of the given problem. So we try to conclude. We try to conclude. So all these basic works, addition, spell checking, searching, okay, multiplication using Excel or MS Word, sorting, or putting graphs and charts. All these problems could be efficiently solved using your classical computer. Okay, so some problem like BQP. So this belongs to quantum category. So factorization, traveling salesman problem, playing Super Mario. Okay, playing is very easy, but predicting the movement of a Super Mario, okay, cutting a stock, so Boolean satisfiability. So all these problem belongs to BQP class, which is very very interesting. Okay, so most of the uh, quantum computer problems are involved over here. Right now, they are focusing this category. Okay, so this problem could be efficiently verified using classical computer, but in quantum, it could be efficiently solved using quantum. Okay, so whatever the problem appears harder for classical computer, the same problem could be easier for quantum. So not all the case, but most of the case. So that is why we go for quantum computers. So some problem like is this Go game and satisfiability. Okay, so these problems belongs to P space, polynomial space or exponential space. So no solution in a reasonable amount of time or space you able to solve that problem. So quantum computer never able to solve this exponential problem or P space problem. So this we need to remember. So not all problems are solved by quantum computer. Some problems are really difficult or really challenging to solve in quantum computer also. So directly I'll go for 1 or 2 slides because we have very limited amount of time. I will share this slide so we can go later. So this topic will take lot of time to cover. So most of the quantum efficiency comes from quantum parallelism. Okay. So two ways we are able to ensure the quantum algorithm is efficient one by choosing the right problem. Okay. By choosing the right problem by manipulating probabilities. So in upcoming class or QT03, we are able to see how to write a efficient quantum algorithm. Okay. So we are able to manipulate probability by doing some mathematical tricks, right? So for that, we are using two major principles, superposition and entanglement. If you properly use, able to achieve the desired result. Okay. So BQP class is a very new type of class in quantum theory. Okay, new complexity class. So people from classical computational theory, it is new for them. Okay, so which is called bounded error quantum polynomial time. Okay, so which is introduced by Ethan Bernstein, and he defined this BQP in 1993. So interested people, please go and refer this paper. Okay, so along with Umesh Vazirani. So there is one important problem, Vazirani algorithm. So go and check after this class. Okay, so both of them laid foundation for quantum complexity theory. Okay, the simple problem like yes or no decision making problem. Okay, it could be solved by quantum computer and it could be solved by polynomial time, but it always comes with some error. So you cannot guarantee using quantum computer. So quantum computer will give you correct result and also wrong result. And errors always come with certain limit. Okay. So right now, if you want to do any research, you can focus on BQP class. So if you want to know more about BQP class, go and refer that website what I mentioned over there. So thank you all for patiently listening to this talk. So we are running out of time. Janani ma'am is also waiting over there. So if you have any quick question, you can post in chat box.
Yeah, participants, please, if there are any questions, you can ask as obviously not yet management joined. So questions if you have any. Thank you, Jaykumar sir, for the wonderful talk, and especially very difficult to explain. Made it very simple. Thank you so much.
Thank you, sir. Thank you.
And within 1 hour, you cover this thing. So yeah, for those who are there, we will look at how the algorithms will be in the next more from and in fact on the programming. So I'll just before
Hello, sir. Thank you for having me here today.
yes, ma'am. Thank you. Yeah, just take 1 or 2. Ma'am can adjust your screen.
Yeah.
Jaykumar sir, thank you so much for concluding your sessions, and we will listen to more in the next course. Lecture we have.
Thank you, sir.
They work together. So
thank you, sir. Thank you. Hi, Janani ma'am.
Yeah.
Hi, Jaykumar sir.
Yeah. So we'll take a minute. Just a slide and other things by that time. We'll just take a minute.
Yeah. Is my audio fine? Like, is it breaking or is it stable?
Audio is. Video is.
Sorry. Okay. For me, on my side, the network is breaking a little bit. I don't know why. When you're speaking, your voice is breaking a bit. Okay. I don't know if it's from my side or it's just
Madam,
the
your
general
voice,
network.
Madam, your voice is fine, but
Okay.
Dr. Shubha Garwai's voice is breaking.
Okay.
So network पे मेरा voice break रहा है. Well, now here.
Yes,
your
voice is still breaking. Your voice is still
You're
breaking.
audible, but it's breaking a bit in between. Not sure why. So.
Okay, maybe there is some issue from our side. Yeah, maybe. Yeah, ma'am, you can share your slides and I'll just introduce you and we can continue. Give me a minute.
Sure, sir. Yeah. Just give. Sure, sir. Yeah, sure.